Think about the devices and appliances around you that are radiating heat all the time. Think about the heat we emit, or the heat emitted from all the noisy cars in Houston. Think about all the factories and industrial plants that dump heat into the atmosphere. 60% of the energy produced in the US is never utilized, and most of it is waste heat. The world's demand for energy continues to increase each year, yet we are still wasting most of it. 30 trillion watt-hours of heat per year are wasted by power plants alone. This is enough to power the entire world for an entire year. Energy is needed to power devices, and this process generates heat. What if we could close this loop by extracting this waste heat and turning it back into useful energy? That's where thermoelectrics comes in. In this video, we're going to talk about converting heat to electricity and the way that thermoelectrics and the Seebeck effect allow us to create useful heat harnessing devices. Now first, we have to meet a scientist named Thomas Seebeck. In the early 1820s, Seebeck found that heating a junction of two different metals made his compass needle deflect. From Physics 101, we know that magnetic fields arise because of currents, so heating the junction must have created a current in the circuit loop. Before we dive more into the science, we should review some concepts that you should be familiar with if you're about to take ELEC 305. And after we go over this, we will be in a position to understand how to best apply this scientific effect in a circuit. In a semiconductor, electrons can either reside in the valence band, which is lower energy, or the conduction band, higher energy. The energy difference across them is called the band gap. If electrons get enough energy to jump across the band, it leaves an empty electron slot behind, and we call that slot a hole. Doping is a powerful tool to introduce extra electrons or holes to a semiconductor material. We have a lattice of silicon atoms, each with 4 valence electrons that contribute to conduction. If we dope this material with, say, phosphorus atoms with 5 valence electrons each, there is an extra electron that contributes to conduction. We would call this type of material N-doped because it has extra negative charges. Instead, we could also add an atom with 3 valence electrons to add holes. This material is now p-doped with positive charges. To understand this better, let's look at the N-type material to the left with excess electrons. If we heat one end and keep the other end cool, electrons from the hot end will become thermally excited and be more likely to migrate over to the cool side. On the other hand, the electrons from the cold side will be slower and less likely to diffuse to the hot side. The result of this is more electrons on the cold side than the hot side, creating a voltage that opposes the thermal diffusion. The same thing happens in the p-type material to the right, this time with excess holes. Holes will also tend to wander to the cold side, but this time, because holes are positively charged, not negatively charged, voltage is created from cold to hot. Using these materials, we can create a circuit with a resistive load. Because of the thermally induced electromotive voltage, a current will be driven around this circuit. This means that power is dissipated in the resistive load. And based on this simple model, we can discuss what types of materials would work best for thermoelectrics. We want the hot side to stay the hot side, and the cold side to stay the cold side. So we want a material with low thermal conductivity. And once the electrons and holes are excited by temperature, we want them to be able to move to the other side to establish a potential difference and move quickly. This means we want a material with high electrical conductivity and mobility. The more electrons and holes we have, the more we can generate voltages. So we want materials that we can dope heavily with excess donors and acceptors. We can take this simple structure and design larger systems that can harness a lot of thermoelectric power. We can apply these simple thermoelectric systems anytime we have a temperature gradient that can be used to generate electricity, whether it's for a watch, a phone, a TV, or a lamp. Let's look at the watch in particular. 1/4 of people who buy a smartwatch stop wearing it after a few months. But what if you never had to charge it? This is one of multiple products on the market that exploit the Seebeck effect to turn heat into electricity. It's called the Matrix Power Watch, and you never have to charge it. It measures calories burned, activity level, and sleep using advanced thermoelectric technology. It's coming September 2017. So there you have it. We can turn heat into electricity using thermoelectrics and the Seebeck effect.